And finally, we get to the crux of the unit, the most important concept, which is going to be broken into two learning objectives, very related to each other. The first is I can use algebraic descriptions of initial and final energy states, along with conservation of energy law, to create a computational model. And then I can use computational model to calculate changes in the energy of one or more components in a system and how they change. The first one is essentially I can create the expression for the conservation of energy and fill in the right values, or not necessarily actually numerical values, but I mean the right sources of energy, and setting the final equal to the initial amount of energy. And the second one is I can use the computational model, essentially that you just created, to calculate a value. So one is basically setting up the problem, and the other one is solving it. So these two learning objectives are in the same process, or going to be assessed often in the same way. So let's get down to business. This is the conservation of energy. The sum of all initial energy sources is equal to the sum of all final energy sources. So the total energy before is equal to the total energy after. Again, we're assuming that this is a closed system, so no energy could be leaving, and the total energy is going to be conserved in a closed system. Let's take a look at an example. Well, let's say we had a 10 kilogram box sliding down a frictionless hill. It's important that we say that frictionless, because then we don't have the force of friction involved. This is a diagram of the situation. You have a ramp set up, and the box starts at a height of 10 meters off the ground. And so that's not 10 meters down the ramp. That would be a different length, which if you do know trig and you knew the angle here, you could totally figure out. But here we're just saying 10 meters off the ground. And what we want to know is what is the final velocity when it reaches the ground? Assuming that it reaches the ground and the ground is also frictionless, it's just going to keep going with whatever that velocity is. So we're finding out what is that velocity. First step, we need to identify all the sources of energy and where some energy values are 0. So for that one, we're going to write the sum of all energies initials, the sum of all initial energy is equal to, and we write kinetic energy plus gravitational potential energy plus spring potential energy plus thermal plus blah, 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 blah. The only source of energy that I can see from this situation starting out, assuming, which actually the problem didn't state, but assuming that the box starts at rest, meaning a 0 initial velocity, the initial kinetic energy is 0. There is no springs involved in this, so that's 0. There's no other source of energy that I can tell. It's not self-propelling itself with some kind of internal combustion engine. Thermal energy, nope. Everything else is essentially 0. So the only source of energy that this object has, the only thing that's going to cause it to gain kinetic energy is by losing some potential energy. In this case, it's going to be gravitational potential energy. So what we could do is write all of these to go to 0. And what we get left with is just that the sum of all energy initial is equal to the gravitational potential energy initially, which is just equal to mgh. Then we got to define all the energy states at the end, at a later point in time. So in that case, here we reached what we are calling 0 height. So height equals 0 at that point. So our gravitational potential energy goes to 0. Again, there's no springs, we're frictionless. Everything else is essentially 0 except kinetic energy. All of the gravitational potential energy is going to become kinetic energy then. And of course, the formula for kinetic energy is 1/2 mv squared, and that velocity final is what we are ultimately after. What we then need to do is write the expression, the sum of all initial energy is equal to the sum of all final energy, and substitute this for what we found up here, and substitute this one, the final energy, for what we found right there. So that's going to be mgh initial is equal to 1/2 mv squared, v being the final velocity squared. And then what we could do is just solve for the final velocity, and what we get is the final velocity is equal to the square root of 2 times the gravitational acceleration constant times the height it started at. Getting to this point right here is essentially the crux of the first learning objective, and then from there it's a matter of just algebraically solving it to find a certain value. And of course, if numeric values are given, you would then plug it into that. One thing that's interesting is you might notice what's not in this expression. Mass. Mass is not in this expression, which would mean that no matter what the mass of an object sliding down a hill is, it's going to reach the same speed after falling the same distance. And this is essentially what Galileo was talking about when he said that if you dropped a feather and a brick, they would fall at the same rate. They would reach the same speed after the same distance. The only reason we don't experience that is because we do have air resistance. And air resistance would cause some thermal energy source. So some of the energy that you started with, some of that potential energy that you started with, would ultimately get converted into kinetic energy and some kind of thermal energy. So because some of it went to thermal energy, the kinetic energy is not going to be as big as if you didn't have any air resistance. So that's another way of looking at the problem of air resistance and how it's going to reduce the velocity of an object after a certain distance. And that's a common theme in this energy unit. A lot of the physics problems that you could have approached with forces and kinematics can actually be solved using conservation of energy as well, as an alternate approach, and sometimes it's easier. Let's take a look at exactly one of those examples. So we have a ball thrown with an initial velocity of 30 meters a second at some angle here. If at its peak, the ball is traveling at 10 meters a second, how high up did the ball go? So what we're trying to figure out is how high up did the ball go? If it started at 30 meters a second, and it gets to its peak, traveling only 10 meters a second, how high up did it go? This problem could easily be solved using kinematics as well. But kinematics can be quite a lengthy process. A lot of equations, a lot of algebra. I'll show you that actually applying energy conservation makes this problem easier than using kinematics, which I'm sure many of you are relieved to hear. So of course, we're going to start with stating that the sum of all energy initial is equal to the sum of all energy final. We are, of course, assuming no air resistance here. As we discussed previously, the air resistance would cause some of the energy that it started with to go into thermal energy, heating up the particles in the air, moving the particles in the air, essentially. And that will cause our calculation to be off. So we're going to assume no air resistance. We're going to quickly identify what are the sources of energy we have to start with. This process gets a little bit faster with some practice. So I can quickly identify we only have kinetic energy. We're starting at what we're going to call zero height because it returns to the same height. It would make the most logical sense to say that the ground is a zero height and there's no springs, there's no combustion engine, there's no electrical energy involved in any way, batteries or something. So this has to be the only source could possibly be kinetic energy. So kinetic energy is the energy that it started with. And then at a later point in time, we're going to have actually two different sources of energy, two different amounts of energy it would have. It's going to have some of its energy stored in kinetic energy and some of its energy in gravitational potential energy because it did go up into the air. So it is now a height off the ground and it's going to feel that force of gravity pulling it down. The last problem, we only had essentially one thing equals another thing on the other side of the equation. So this time we got a little bit more complicated. If we break off what these kinetic energy and potential energy equations are, we get 1/2 mv initial squared is equal to 1/2 mv final squared plus mass times gravitational acceleration constant times the height. Now, before you go on any further, in a physics problems, you should always try to find where you have zero values, which we've already done. And you should also try to find where you have common factors that you could either factor out or divide out of an entire equation. And here we have one of those instances. This is the same object. Its mass is the same. So every single term has mass involved, means we can actually get rid of the mass. Now remember, every single term needs to have it in common as a factor for you to do that trick. So we can just get rid of the mass, but what we can also do is we have a half equals a half plus something that's not a half. Well, we can multiply the entire equation by 2 in order to cancel the fractions. And what we get is the initial velocity squared minus the final velocity squared, because what we did was move the final velocity squared over to the other side using subtracting final velocity squared, is equal to 2gh. What we're doing is we're trying to solve for the height, so we're just going to divide by 2g, 2 times the gravitational acceleration constant. And we get an expression, which is the height the object reached equals the initial velocity squared minus the final velocity squared divided by 2 times a 9 gravitational acceleration constant. Here's where I need to specify something. Previously, when we declared g for forces or for kinematics, we said it was negative 9.8 meters per second squared. For this one, there is no negative on this. This is essentially the absolute value of the gravitational acceleration constant. So we're not going to plug in a negative sign for the 9.8 meters per second squared. The only time you're going to plug in the negative sign for the 9.8 meters per second squared is when you're doing kinematics. And that's because you're setting the acceleration to be in the negative direction because you're saying that going down is negative. So g is just a value of 9.8 meters per second squared. It does not inherently have the negative. It's just we often apply a negative to it because we're declaring going down as negative. What we get is 900 minus 100 divided by essentially 2 times 10. And so in the end, if we do some approximations like that, using 10 meters per second squared instead of 9.8, we get about 40 meters. Overall, this process, I think, personally, is much easier than using kinematics equations to solve the same problem. Let's take a look at another problem. This one, a 1,000 kilogram car is initially traveling at 30 meters per second. It then applies the brakes until it comes to a complete stop. The first question we want to ask ourselves conceptually is, where did the energy go? If the conservation of energy can be applied in this equation, then no energy can be destroyed or created. It can only be turned from one form of energy into another form. So what form of energy gets created? Well, not sure if you know this, but when cars apply the brakes actually get extremely hot. So in this case, kinetic energy is going to be transferred into thermal energy. So the sum of all initial energy equals the sum of all final energy is, of course, the conservation of energy expression. The initial energy that the system has is just kinetic energy. And at the end, when the car is stopped, it no longer has kinetic energy. It no longer has gravitational potential energy. We're not talking about springs or anything or batteries. So the only source of energy left is thermal energy. So all of that kinetic energy gets transferred into thermal energy, which means if we were to ask how hot did the brakes get, we could figure out at least how much thermal energy got added to it. And that'd be simply as just writing 1/2 mv squared is equal to the thermal energy. So that's going to be equal to 1/2 1,000 kilograms times the initial velocity of 30 meters per second all squared, which gets you about 500 times 900, which I believe is about 450,000 joules. Now, that's not telling you how hot did it get in terms of temperature, because, of course, if someone was asked how hot it gets, most people think temperature. But you can figure out how hot the brakes might get if you apply the equation that at least I usually teach in my chemistry class of the heat energy that goes into or out of a system is equal to the mass of an object times the specific heat of that object times the change in temperature. And what you can do is just find that change in temperature. So you get the change in temperature is equal to the heat energy added, which in this case is our 450,000 joules, all divided by the mass of the brakes in this case times the specific heat of the brakes. So for that one, you would need to know what the brakes are made of in order to solve the rest of this. But you can at least say how much thermal energy was added to the brakes.